telescopes at all. And basically you notice that when a beam of light comes in and hits a mirror, it reflects off at an equivalent angle. So the rule is the angle of incidence, which is here, is equal to the angle of reflection. So that simple fact actually underlines the way all reflecting telescopes work. So if we go to the next one, whoops, went the wrong way. Okay, this is the other little optical fact that we use for building or designing a telescope. You see again we've got a ray of light. This time instead of hitting a mirror, it's hitting a transparent surface, probably some kind of glassy object there. And you see the beam of light comes in and then it gets deflected. And that's called refraction. So the angle of incidence and the angle of coming out the other side is not obviously the same as the reflection rule. But you can see this if you like put a stick into a glass of water or a pencil. You notice that the pencil below the water looks as though it's bent. And so it's using that property of light moving from one medium to another. And you notice there's also a fainter ray which is reflected, and this is a property of when you move between two different mediums, some of the light goes through, but some can also get reflected. So that's a bad thing generally for telescopes, or any kind of optical device. And I won't dwell on this, but this is the formula for how refraction works. And basically the two different substances the light's travelling through have a property called refractive index. And what happens is when you move from one medium to another, the speed that light is travelling in that medium changes, and that's what causes the change of direction. So basically in a vacuum, speed of light is always the speed of light, but in other transparent things like glass or air, it can be different speed, and the change of the speed of light is actually what causes the refraction. So if you did optics at high school, probably something they do in what be last year, they do that sort of thing in physics. Right, and there's one other thing which for telescopes is a bad thing, but it's actually useful for science, is that with refraction, is that light going through something like any kind of glass, like a prism. Unfortunately, the refractive index is different for each colour, and so you get this rainbow effect. Like you can see that the violet is bent more than being refracted more than the red, which is here. That property of glass actually allowed scientists like Newton to actually investigate the properties of light. We know about, if you've probably been attending the lectures on Introduction to Astronomy, where they talked about spectra. It allows you to determine a lot of information about the source of the light, like what it's made of, things like that. But generally, for a telescope, that's bad, because you don't want the light spreading out like that. And this is just showing you there's a number of different kinds of glass, and you can see along the bottom it shows the wavelength of the light. So the shorter wavelengths are bluer, and then the longer wavelengths are heading towards the red. And you can see the graph is showing that for any given kind of glass, like that gives you flint glass, different types of crown glass, that the refractive index not only changes with the type of glass, but also the colour of the light. So unfortunately, all glasses we know of do this. So if we had a glass that didn't have what's called dispersion, in other words, where the refractive index is different with the colour, you'd be able to have really superb lenses.
Yeah. Okay,
so this is what happens. The first refractor invented by various opticians in Holland. Nobody knows for sure who, because there was a patent dispute over who actually made the invention. A guy called Lipperhay made probably the best claim. So what you see there is that they came up with this idea of a piece of glass. In fact, the early ones were only curved on one side. It was too much work to do the other side, so they would tend to have a flat lens on one side and curved on the other to form their objective lens. And you can see the rays of different colour entering the lens. And you notice they all focus at different points. You've got the blue there, the green, and the red. So that's obviously not going to be very nice when you're viewing something, because you have one colour in focus and the other colours are out of focus. The way they got around this was by having quite a long focal length, because the error was still there, but you didn't notice it so much. You weren't bending the light as through such a steep angle, so you could get away with it. In fact, some of the early refractors, they got really ridiculous. They had to have an objective lens held on top of a mask, and then you'd hold the eyepiece many metres away and try to position it in the right place on a stand.
Is this what they use for these glasses, for the colourblind people, to move the focal also?
Oh, that's possibly how they work here, because then, well, I'm not sure, because the changing the focus doesn't change the colour of the light, so that might be something different. So generally the term for this problem is called chromatic aberration. Basically anything called an aberration in optics is bad.
Yeah.
So after a while, in the 18th century, Chester Moore Hall and the Dolan family, actually not just John, but I think the Dolan family came up with this idea that if you combine two different kinds of glass together, you could actually help with this problem. And you can see in the picture here, it shows two lenses. One is a crown glass and the other a type of flint glass. And the effect of it is that they have different refractive indexes. So you can see the blue's getting refracted a lot, but when it exits, it aims so that it crosses with the red. So the optical designer can play around with the type of glass and the shape of the lenses and so on to bring two colours to the same focus. But unfortunately, the green is still out of focus there. That's not normally the way visual lenses are designed. They would normally aim to get the red and the green into focus, because your eyes are most sensitive to those colours. And if you get this type of telescope called an achromatic refractor, and you look at something bright like the moon or Sirius in it, you'll see that it has a purple fringe around it, and that's because the violet is out of focus. So what can we do about that? Well, if you spend lots of money, you can go to a lens like this. These are actually a lot more common now than they used to be, because the glass types are getting cheaper, and people in Taiwan and China are making more cost reasonable versions of these lenses. So what happens with this one? Complicated arrangement of lenses, and you can see the different colours follow different paths through the lenses, but they all end up in focus at the same point. And whether this be a telescope lens or a camera lens, this type of lens is referred to as apochromatic, which means that all the colours come to focus at the same place, and you get a very sharp and high quality image. And people love these for viewing planets and moon and things like that. For deep sky, they're a problem, because for a deep sky you want a bigger aperture, and this type of lens is still very expensive when you go to a large aperture. Like I think I was reading a company called TEC that make 7-inch version of this type of lens, and they were something like $20,000 for a 7-inch telescope. But yeah, they are a lot more available than they used to be. And the way they achieve this is that normal crown and flint glass can't be combined in any combination to do this. So they have to use these more exotic glasses, such as this one. Here's an example of O'Hara FPL 53, which is O'Hara, isn't it? Is actually Japanese, not Irish. So it's a Japanese company that specialises in optical glasses. And the material calcium fluoride is sometimes used as well. The problem with that is that it's very soft, and so you never, if you put calcium fluoride into a lens, you never make it the front element because it would be too easy to damage. So when that's used, it'll be on one of the two internal lenses. Okay. So this is just comparing the two, talking about the price. You can still get really good views with an achromat, which only brings two colours to focus. What some people do to get around, if they don't like the violet filter fringing, you can actually put a filter on to basically block the violet, and you can get quite a good view that way. Alright, so the another solution to this problem with chromatic aberration is to not use a lens at all. So Isaac Newton worked out that you could focus light using a mirror and make a telescope using mirrors. So this was his design, called a Newtonian telescope. So you have the star that you're looking at over here somewhere. Light comes through the tube, reflects off the mirror using that angle of incidence equals the angle of reflection. And because the mirror is curved, all the reflected rays end up coming to a point. So the mirror is effectively acting like a lens. So one thing about reflection is it's not dependent on the colour. So all of the different colours come to the same focus. So it's really simple. It takes away the problem of chromatic aberration completely. Problem is, in Newton's time, they didn't have a really good way of making mirrors. What they used to do is just have like a polished metal, like a shiny metal. Sometimes they had an alloy called speculum, which you could polish up and make it quite a nice mirror, but it would degrade very quickly. So this meant that this wasn't, for a long time, this wasn't popular, even though you solved the chromatic aberration problem. And it's probably easier to make this kind of telescope than a refractor with lenses. I've gone the wrong way again, sorry. Okay, so apart from the reflective surface on the mirror, we've got some other issues with the Newtonian reflector. If the main mirror is spherical in shape, then you find that if you trace out the rays, by just using the angle of incidence equals angle of reflection rules, you find that they don't actually focus to a point. And this kind of error is called chromatic aberration. And if you ever change the shape of a mirror to a parabola, so if you talk to Andrew, if you're buying a Dobsonian telescope, the main mirror knows is shaped as a parabola, and that gets rid of this spherical aberration problem. So you still have one residual problem with a simple Newtonian, is that as you get away from the centre of the image, you get an effect called coma, and that is basically tends to smear the star images out at the edge of the field. As long as you haven't got too fast a focal ratio, it's reasonably acceptable. And you can get what's called a coma corrector, which is basically an optic that you put in the focuser, which corrects the coma. It's a refractive element though, so you're getting away from a pure reflector. But these can work incredibly well if you have seen any of Rob Folson's work in astrophotography. He has a homemade Newtonian reflector, specially designed for astrophotography, and he does use a coma corrector with it. And Raymond Collicutt, he specialises in planetary photography, where the coma doesn't really matter because the planets are small, so they're right in the centre of the field. Typically, if you're using like an F ratio of 6, and I'll explain what that is later, which is the sort of Dobsonian telescopes that Astron sell, the coma is not really noticeable for visual use, but you will if you're taking a photograph, you'll see the effect on the edge of the field. So some other designs. This one isn't so common for amateurs nowadays, but designs based on this are quite common. So this guy was Cassegrain invented this type of telescope, and we have one up in the dome up there. The Zeiss EWB Zeiss telescope uses this design. And basically what you do, instead of having that secondary mirror like on the Newtonian, which was a flat reflecting the light out the side, where you put the eyepiece, this one reflects the light back through a hole in the primary mirror, so you can have your eyepiece at the back of the telescope. So these are a bit more complicated because, as well as having a parabolic primary mirror, the secondary is actually a hyperbolic shape, so it's a bit harder to make than a flat mirror that's used in the Newtonian for the secondary. Gives quite good images, so a lot of you would have seen through the Zeiss on a clear night. But they're not really popular these days. So this is another variation of the Cassegrain reflector. So it's called a Refraction, and Astrons are selling these too, other scope manufacturers. It was worked out that if you had both the primary and secondary mirror was hyperbolic, you could completely get rid of the coma across the field. And so virtually all of the professional telescopes in the world use this design, including the Hubble Space Telescope. And they're now available for amateurs, which they used to be. A little bit expensive, but if you, especially if you're into astrophotography, these scopes work really well. I think that might be one of Andrew's ones there. So we come to the third kind of telescope, which is basically a hybrid between a reflector and a refractor. So you have a combination of reflective and refractive elements. And probably the most common one these days that amateurs have come across is a Schlick Cassegrain. If you haven't seen one, we can have a look afterwards. There's several of them in the room down there that they use for public viewing sessions here. And the other sort is called a Magnification telescope. The Society actually owns quite a big one, and a 12-inch one, but it's not in use because we haven't got anywhere for a home for it. It probably needs an observatory because it's not an easy thing to move around. So we've been looking for a home for that telescope for a while. So this is how the Schmidt-Cassegrain works. You have a look, it sort of looks like the other kind of Cassegrain, except you notice that in front here there's actually a glass plate. And that's not just like a window, it actually has an optical effect. So that helps to remove some of the optical aberrations and allows you to use simple spherical mirrors for both the primary and secondary. It looks as though the rays are going straight through there, but you can see there's just a tiny deflection, and that's enough to create most of the optical aberrations that you normally get with spherical mirrors. So this type of scope is cheap to make relatively, and so that's why they're so popular from me and Celestron and other people make this type of scope. And of course, because of the folded design like that, you have a relatively short tube. One thing I didn't mention, a problem with refractors is that they tend to get very long, so it means they're awkward on a mountain. So you see the secondary mirror there is actually mounted in a hole in the corrector plate. Somebody brought one of these in recently to the start and left it here, and I'm not sure where it came from. It quickly decided it wasn't going to be that good because when you turned it up to see it in the corrector plate, it was smashed. So not very nice. So a Maxitoff is slightly different again. It also has a corrector, but instead of a thin plate that does a very small amount of changes, the Maxitoff has quite a thick, it's called a meniscus lens, so it's much thicker than the corrector plate, and it's got the same curvature on both sides, so it's relatively easy to manufacture, but it's quite a big chunk of heavy glass, so it does make the telescope heavy. And the other thing is, what they do is the secondary mirror is actually you just silver the back of the meniscus lens, because it turns out the back side of the meniscus is exactly the right shape to correct most of the aberrations for this type of design. So, as I said, the Society actually own one of these, but it hasn't been in use for quite a few years. But these type of telescopes give excellent images. They just tend to be quite cumbersome, very heavy.
What's that red sign down at the focal point there?
Oh, I think that's just showing you showing you an image, just where the image forms. I don't think there's anything special about it.
Are these two different focus points?
What that's doing is showing that whatever you're looking at in the sky has got a finite size, so angular size, so it's just basically showing how a particular, like a planet or whatever, would form an image if it covered finite size on the sky. The star would always focus to a point. Well, you'd hope so anyway. Right, so eyepieces. So the other thing, generally if we're using a scope visually, you not only want the telescope, you want to use an eyepiece to actually, so you can see something. These diagrams look pretty complicated, but because I've got a lot of rays on them, just explaining how things work. But the top one is basically showing the very original type of eyepieces used by the Dutch spectacle makers that invented these telescopes, and also Galileo used the same type. And you notice that the eyepiece is actually a negative lens, so it's concave on each side, or sometimes it will be concave on one side and flat on the other. That type of eyepiece will give you an image that actually is the right way up. So this diagram here is showing you that the image is the right way up. But the problem with it is you get a very narrow field of view. So it's kind of like looking down a drain pipe. So another well-known astronomer from around the time, Kepler, came up with the basic idea of the sort of eyepieces that pretty much all eyepieces today are based on, called the Keplerian scheme, the Keplerian telescope, where you have a positive lens. And this will actually reverse the image. So whatever you're looking at will get flipped over. But Kepler reason why it's in the sky, it doesn't really matter which way up it is. So the advantage is that you get a much wider field of view. These are still really basic lenses. When we get to real eyepieces that we use today, the designs are a lot more complicated. So just some facts about eyepieces. One of the big things about them is the size of the barrel. And so if you've got a telescope, your focuser will have a barrel size that fits certain size eyepieces. And there's 3 standard sizes. If you've got a 0.965 one, then you've probably either got a toy telescope or a very expensive Questar one that aren't really made anymore, but they used to be quite popular back in the 1970s. And they had a screw-in eyepieces of this size. But since then, the only telescopes that have used that size have really been what we sort of call department store telescopes. So they're really poor quality ones. So generally, you either have a 1 1/4 inch eyepiece or a larger 2-inch barrel size on your focuser. The 2-inch eyepieces size is becoming more common, and of course if you've got a 2-inch focuser you can always use a 1 1/4 inch eyepiece because you just have an adapter. Unfortunately it doesn't work the other way around. If your focuser is only 1 1/4 inches, then you're out of luck trying to use an eyepiece with a 2-inch barrel. So the key, I guess, parameter of an eyepiece apart from the barrel size is the focal length. So this is how we change the magnification when we're viewing. If we have a longer focal length, the magnification is actually lower. So I think one of our members, Gareth, when he was doing public outreach, he'd always show them 2 eyepieces, and there was this big one, and we'd show them the small one, and he'd say, which one gives you the most magnification? And generally the public will point at the big one, but in fact it's completely the opposite. So you can set the magnification to your choice by choosing a different focal length eyepiece. There's one other parameter, which is called the apparent field of view. So what this is, when you're looking through the eyepiece, it's not how wide you see really on the sky, but it's how wide it looks, how much you can look around to see the view. And generally, typical eyepiece used by amateurs are called a Plossel eyepiece. That will give you about 56 degrees of apparent field. If you go to Astronomy Super View, they're about 68 degrees. Then you get ultra wide angle, which is about 82 degrees. And then you get these latest sort of designs that will give you 100 degrees of apparent field. You think the wider angle you'd want the better, but there's some specialist eyepieces that have quite a narrow field, 40 degrees, which are designed purely to have almost perfect optical performance, but they only work at a very narrow angle. But people who do planetary observing love those eyepieces. But you really need a tracking mount for them, because otherwise whatever you're looking at will drift out of the field very quickly. Right, and here's some of these advanced designs just to show what goes into them. The reason why if you ever see one of these eyepieces, why they're so big and heavy, because they have an awful lot of glass in them. So Alan Naylor sort of astonished the amateur community back in the late 1980s when he introduced the Naylor range of eyepieces, which you can still buy today. And they were quite good if you had really deep pockets. They generally cost as much as a telescope. So that was the Naylor Type 2, and you can see we've got 1, 2, 3, 4, 5, 6, 7, 8 individual lenses inside the eyepiece to create that wide field of view and have no aberrations. And then a more modern design also from Tally Group called an Ethos, which is even more expensive. And they give you an apparent field of 100 degrees. And they work down to, that number there is showing you the focal ratio of the telescope that they can work down to. So they obviously work if the F ratio is longer. If you've got a fast telescope with f4.5, these will still work really well. If you go faster than that, like a really fast f4 telescope, if people do astrophotography, you know what that means. It's staying quite fast lens. Then even these eyepieces will start to have a problem. Okay, another accessory that amateurs really often use is a thing called Barlow lens. And this is a negative lens, but not one that's designed for looking through. Instead, this isn't really to scale out this way, but you can see the rays come down here at an angle, and then instead of continuing on to the focus, they actually get deflected, and it brings the focal point way down here. So the reason for that is it makes it appear in a way, so doubles the effective focal length of the telescope, which also doubles the magnification with any eyepiece that you pair it with. So the reason you would do that, there's two reasons. If you haven't got a lot of eyepieces, you can have a Barlow, combine it with an eyepiece, you basically double the range of magnifications you can use. These are actually also useful for photography. So if you're imaging a planet or maybe the moon and you want to get a really close-up view, then instead of just putting your camera on the telescope, you put a Barlow lens, makes the image scale bigger.
The telescope scale itself only has two lenses, hasn't it? Like that one and that
Well,
one.
in this example, this works with any kind of telescope. It could be
What that means?
that's like a pretend objective. So if we come back to here, to the person looking here, it's as though the objective was really way out here. So this is actually closer together than it should be. It's as though the eyepiece is being used with a telescope where the objective is a lot further away and a longer focal ratio. That's the effect of putting a negative lens in the chain like that. So it effectively makes the telescope appear to be a much longer focal length. Okay. Sometimes you want to do the opposite to a Barlow lens, and this is people that do, this is really only for photography, is where you don't actually want a really narrow field on your camera, so you actually use a focal reducer, which is the opposite of a Barlow. Instead of effectively making the focal length long, you want it to make it shorter, so that you can actually get more of the sky onto your chip or film or whatever. So the other thing that this does is it means you can use shorter exposure. Do you use one of those, Trevor, a focal reducer? Yeah.
Otherwise, stars are better.
Yeah. Right, and this is getting a bit more esoteric, but it's something that if you're into photography you may have to use, because you wouldn't even notice this problem visually, and this is highly exaggerated, but a lot of telescopes, we sort of talk about the image plane and you realise that in a camera the sensor is flat, but the image plane of a telescope isn't necessarily flat, it could actually be curved, like when a star further away from the centre is actually focused at a different point. Now you don't notice this when you're looking because your eyes will automatically adjust when you're just viewing, but the camera will definitely notice. I mean, you'd never get a telescope like that with a field curvature that extreme, but for photographers they will notice it, and what it means is that the stars might be nicely in focus at the centre of the image, but they're slightly out of focus up in the corners, and that can be really annoying. So quite often this field flattener and a focal reducer will be combined into one into one optical device, and the problem with them is that they have to be matched to a specific telescope. Well, you can't buy a generic one, so it has to match whatever your telescope is. Right. More accessories this time, filters. Now these can be great for visual observing. The most obvious one is called a neutral density filter, or sometimes just called a moon filter. And all this one does is to cut out the glare by blocking the light, but it blocks it evenly over all colours, so it will give you a dim view, and that's really useful if you're looking at the moon. Because the moon, if you look at the moon in a telescope, it's incredibly bright and you're almost dazzled by it. So actually useful for Mars as well at this time when it's really bright. You'll notice if you look at Mars in your scope, you'll be quite a lot clearer when it's close to opposition. Another one is there's a commonly used one that's called an O3 filter. That's really good for certain types of nebula. It really brings out some of the detail in the nebula. So, and the UHC filter, yeah, that's, if you've got sodium vapor lights around that are lighting up the sky, this will actually block fairly narrow bandwidth of sodium, so it takes the sodium glare away and helps around the city. Unfortunately, the utility of this type of filter is going to disappear soon because they're rapidly replacing them all with LEDs. So all the high pressure sodium lamps, which you can filter out, are being replaced by LEDs that you can't really do much about. And just a standard warning, none of these types of filter are suitable for looking at the sun. So you need a proper full aperture solar filter if you're doing solar viewing. I've got I'll just go through this reasonably quickly because there's a lot of definitions here. I forgot I was going to print some of this off. It might be useful as a handout. But there's quite a lot of terminology we use with telescopes. So the first one is a capital D. That refers to the aperture size of the primary lens or mirror. So basically bigger is better, right? And the reason is that that formula there refers to the angular resolution. So the bigger D is, the smaller the angle is that you can resolve. So if I double the angular resolution, then this thing here gets smaller, so I can see more detail. So that's why astronomers, one of the reasons they want a bigger size mirror, you can resolve more detail. The other reason, of course, is that you're gathering a lot more light, so you can go a lot fainter as well. So the bigger aperture is better for both of those reasons. So the next one is the focal ratio, that's a capital F. And that's basically the ratio between the focal length of the telescope, which is basically the distance between that the light cone travels before it comes to focus from the objective. And of course we can play around with that by tuning it into effective focal length using curved secondary mirrors and other lenses and what have you. But so we divide the focal length by D, and that's the focal ratio. And for example, we're talking about one of those F6 top sodium, so the focal length of one of those is at 1.2 metres, and diameter 200 millimetres, so that's where we get the F6 from. We divide the diameter 200 into 1.2 metres. If you're familiar with cameras, you can actually change the F number. The camera lens will have a diaphragm on it, and basically you don't always have that diaphragm opened up full. So depending on how much light there is and what you're trying to do, you might wane the aperture right down. You never would normally do that with a telescope, because you always really want the aperture open as wide as possible. Occasionally we do it though. If some people, instead of using a moon filter, you can actually put a cap over the main lens with a hole in it. Basically stop the telescope down to cut out some of the glare. But
Yeah, that's actually, I've got one on my 4.5, which is for solar filter.
yeah, right. Sometimes for viewing the sun you'll do this rather than using the full aperture of the telescope. You have a cover with a hole in it and you only put the solar filter over the hole. So, right, we talked about the focal length of the eyepiece. The apparent field of view is how wide it appears when you're actually looking through the eyepiece. The true field of view is how much of the sky are you really seeing. So, you know, if you can see the moon and it exactly filled your view, then that would be half a degree or 30 arc minutes. That is the true field of view in that case. Another thing which probably, I don't know whether Andrew brought any binoculars in, you can try this yourself, it's called the exit pupil size. And what this is when you, like if you hold binoculars up to the light, you'll see hopefully a round spot of light in the middle of the eyepiece. That's the exit pupil. And the size of that does matter to some degree. If in the case of binoculars the exit pupil is bigger than your eye's pupil, then when you're using the binoculars at night, you won't be getting all the light into your eye. And this is a problem for people when you get older. Your actual eye pupil doesn't open as wide, so you're actually going to be blocking out some of the light that the telescope or the binoculars is providing you. So it does mean that you may not be able to see as faint an object as you could when you were 20 years younger or whatever. And eye relief is something that's important for people who wear glasses, especially if you want to view wearing glasses. If your eyepiece has a short eye relief, and this is to do with the optical design of the eyepiece, then you can't actually get close enough to get it into focus. And even if you don't wear glasses, they can be quite uncomfortable to use because you have to shove your eyeball right up against the eyepiece. So generally people like eyepieces that have a longer eye relief because they're just a bit more comfortable to use. And then this number M, of course, is the magnification. So, a couple of formulas. Time. So, I mentioned this before. The focal length of the telescope is the aperture diameter times the F number, or you can do it the other way around. The F number is the focal length divided by the aperture. So it just gives an example here of one type of telescope. Magnification, so is the focal length of the telescope divided by the focal length of the eyepiece. So it just gives an example here. I'm using a 25mm focal length eyepiece. Divide that into the telescope focal length means 48 times magnification. So if you don't know the focal length of the eyepiece, then it's a bit tricky. Hopefully it's written on the barrel by the manufacturer. Otherwise it's quite hard to work it out. Just from doing measurements or whatever. And this is just how the true field and the apparent field are related. So this gives an example of a Plossl eyepiece, which is fairly common when used by amateurs. The apparent field of view about 50 degrees, varies a little bit depending on the exact design. And it gives an example here that if we we're using that same telescope on the previous slide with a 25mm eyepiece, 50-degree apparent field, then the true field will be about 1 degree. So you can use these formulas to figure out what any given eyepiece and telescope combination will let you see in terms of the actual size of the field you can see on the sky. And you see if you increase the magnification, your true field is going to get less. So higher magnification, less field of view. If your scope isn't tracking, then things are going to drift out of the eyepiece faster.
I've got a, but I've got something the same as what you've got there.
Yeah.
It's got a 30mm eyepiece.
Right. Right, well you can apply that same formula with have a slightly
Yes.
wider field of view, but it also depends on the apparent field of view, and that's a design issue, the manufacturer design. So I mentioned like a TeleView EFOS eyepiece will give you a 100 degrees apparent field, you plug it 100 into that equation.
Yeah.
So if you're using a TeleView EFOS, you'd plug in 100 there,
Yeah.
and so you get 2 degrees out of that eyepiece.
Yeah.
So even though the magnification is the same as the throttle, you can, that expensive eyepiece will show you twice as much real estate on the sky. And that's why you pay the big bucks for those eyepieces, I guess. As well as the fact they have superb optical quality. That's just a bit of guff about, if you didn't know, you could actually work in reverse. And I won't bother reading that out, but just by explanation, if you don't know what the true field is because you don't know the apparent field of the eyepiece, you don't know the focal length, what you could do is pick a star near the meridian and set your telescope up so the star is just crossing the field, and leave your telescope not tracking and basically time how long it takes to cross the eyepiece. Because we know that stars move how many degrees per hour across the sky? It's about 15. So in 24 hours it does a complete circuit of the sky. So if you were really keen to know, most people wouldn't care, but you could calculate it backwards by actually timing how long a star takes to cross the field of view. Anyway, we've now got how you work out the exit pupil size. So that's the focal length of the eyepiece divided by the focal ratio of the telescope. So an example here, 30mm colossal f6 telescope, so the exit pupil will have a diameter of 5 mils. So why does this matter? If you were to use a 40mm eyepiece, the exit pupil will probably be bigger than most people's eyes. So it means that some of the light isn't actually getting into your eye from the eyepiece. So it won't mean anything except that you're not getting the full benefit of the eyepiece. Some of the light is going to waste. So generally if you're younger, your eyes will have a bigger entrance pupil when you're dark adapted than somebody who's older like me.
There are chemicals that you can use to enlarge the pupil of the eye.
Yeah, we've got a really good thing to stuff.
A lot when I go.
They may cause other issues with
It's not like focus.
Like magnification and enlarge people with diabetes to hear the chip in my eyes.
Okay, so that's it. Probably we need to have another session about the other, what's probably the most important accessory to use with a telescope that we didn't really discuss at all. Anyone think about what that is? The mount.
Yeah.
So that's probably a talk for another day. So are there any other questions? If anyone's interested in those formulas and stuff, I actually have a sheet or think about on like an email. If you just Google it, there's plenty of sites on the internet It had all of that information.
Mm.